Okay, so what we were going to do here is play Tangled, and we're going to play against a very capable Monte Carlo tree search agent. So this graph, I just want to make sure I got all my stuff ready here to go. Yeah. So this graph is let me get it right. It is the second Blanusa snark. I'm probably pronouncing that wrong, but it's what you're looking at. It's got 18 vertices and double check 27 edges. And I am playing red, and Monte Carlo Tree Search Murray over here is playing blue. And I'm playing a variant where instead of the players placing their token on one of the vertices to claim it as their color, instead this variant fixes your token to be in a specific location, in this case mine on 0 and blues on 1. There's some evidence from some of the experiments that I've been doing that this is actually better than allowing a player to place their token in terms of making the moves that you make throughout the game more meaningful. I had this suspicion that if you could place your token whenever you wanted, the best strategy is always to wait till the end and then evaluate whatever the game board is and then choose your vertex depending on that. If you've got a fixed location, obviously you can't do that. And the only thing that matters to the eventual result is which colors the edges are, which makes the game simpler, and also I think it makes it better. So I have set this up so that the player I'm playing against is very good at this game. I'm using 1,000 rollout pure Monte Carlo tree search, so there's no neural nets or anything on this one. And one of the consequences of the way that Monte Carlo works is at the beginning of the game, it takes longer for the player to determine what to do because all of those rollouts, there are a lot of leaves that aren't terminal states when you first start rolling it out. So the way this is going to go is I'm going to kind of do a play-by-play on the moves, but I'm going to fast forward a little bit through the waiting time for my opponent to make his move. So if I was actually doing this in a real setting like a tournament or something, there would be a timeout where you couldn't take forever to make a move. And also the Alpha Zero variants are much faster because you're relying on the neural net to make your moves, and the forward pass through the neural net is really fast. So this is a slow but good player. And part of the reason why I wanted to show the very good player is to try to see what moves they're making and try to understand why. Because this game is so new, it's kind of difficult to figure out how to play well. So I'm going to start, and my strategy is to try to build a clump of territory that I own by painting the edges that are associated with, or next to my vertex green, which is trying to build like a little ferromagnetic clump, a clump where all of the spins, the values of the vertices are all aligned with me, which is what I want, because I want high influence, which means I want high correlation to whatever direction the spin on my vertex is pointing. So if this is up, I want them all to be up. If this is down, I want them all to be down. And the way we get that is, at least the obvious way, is ferromagnetic interaction. So I'm going to play here, green, and that'll be my first move. There we go. Okay. Again, for reasons that I have absolutely no idea, our competing agent decided to color the edge between 9 and 12 green, which means these two are going to want to be aligned. And So what I'm going to do is I'm going to color this one green because I want like all of this to be me. So I'm just going to color this one green. Okay, so the AI agent has placed a green edge between 5 and 1, which I kind of get because that's kind of what I was trying to do over here. So I'm going to continue. By the way, I should mention that the Monte Carlo tree search proceeds by doing rollouts which have to evaluate terminal states. So this agent is constantly having to ask, who won a game. And the way that the adjudication is done in this particular example that I'm showing you is using simulated annealing with 1,000 samples. So 1,000 isn't a lot, but it turns out that the simulated annealing terminal state evaluation for a pure Monte Carlo agent dominates the runtime. So if I was to increase the number by a factor of 10, it would take 10 times longer for the entire agent to make a decision. And I think it actually does matter. Like if you were doing this for real, you'd probably want to do more than 1,000 samples. But at least when we're just exploring and poking around, it probably doesn't matter that much. You're going to miscalculate some terminal states, and there's also the obvious thing that what we're hoping is that simulated annealing, which gives you some type of biased sample over the low energy states, doesn't actually give you the same probability distribution as doing the quantum quench does. So the quantum quench is like inherently a non-equilibrium thing. So when you get to the final state, you are sampling from a distribution that's probably not the thermal icing distribution. Anyway, a lot of words there. Okay, so I'm going to continue with my strategy of trying to build a ferromagnetic clump. So I'm gonna put a green here. So he is following the ferromagnetic clump idea, has put a green edge between 17 and 1. I'm just going to continue with doing my thing. I'm going to put green here. Okay, so here we go. It's clump versus clump. So we're still far enough. Oh no, we're not. We're actually only one away here. So this stage of the game, we now have clumps that are connected, and there's an option of connecting them. Like if I was to play here, then his clump and my clump are now connected. So if I play purple here, what that means is that we're going to be opposites. So let's say all of these are up and I put purple there. That would mean all of these would be down. So all things being equal, I would have more influence because I have 1, 2, 3, 4, 5 that are in my clump, and he only has 1, 2, 3, 4 that are in his clump. So if I put a purple there, at least for the time being, I would always have more spins agreeing with me than he would. So I'm going to do that. I'm going to play purple here. Okay, so he now played a purple here. All right. Doesn't look dangerous yet. But we have to start thinking about it because... Oh, wait. Right. So there is an edge actually that connects this guy to the other clumps. So if I'm all up, then that means down. So that belongs to him. So if this was yeah, it's a little bit hard to figure out. So this outer hexagon, if I'm up, so that's 1 up, 2 down, down, down. So 3 downs, 2 ups, down. That's 4 downs. So it looks like I'm losing this outer hexagon, I think, no matter what. Because up, up, so that's 2 for me. Down, down, down. This is down 2, yeah. So this was actually a really good move for him because there's nothing I can do now to salvage, say, just winning the outer 6 vertices. I've kind of lost them. But that's okay. I think it's fine. So what am I going to do now? I'm just going to keep building my my ferromagnetic clump up, and I think if I play green here, I'm all right. So I'm just going to do that. So him playing green down there between 2 and 3 kind of locks in his dominance of the outside. But now if this is up, down, so this is me, him. I'm going to paint this one purple so that this clump is for sure me. So I'm going to paint this one purple. So this purple here, connecting 16 and 14, means that if this is part of my clump, so this is up, this would be down, so that would be him. This is me. So if I put a purple here, this is for sure him, but then that means this is for sure me. So I think that's good. So I'm going to color this one purple. So let's see. So there's now that has grown his clump. Okay, so if this is up, I want to make sure that I've got 1, 2, 3, 4, 5, 6. So that's not very many. Definitely not ahead right now. So let's try to make some inroads into cutting off this cluster that he's got. So I'm gonna paint this one purple to try to have 15 start to look like it might be mine. And he's played green there, which makes sense because this one is owned by him. So now this one is also. So this is him, this is me. Him. So let's paint this one purple, which I think reinforces my ownership of 15. And this one is voting for 7 being his because this one's mine, so that one's his. This one's also his. So we might be able to flip one of these two. I'm going to put a purple here to kind of weaken the strength of these both being owned by him. He played up here, growing his clump, which makes sense. So let's see what's still in play. 13 is still in play. So if this is his, I want this to be mine. I'm going to paint this one purple. And he put a purple there, which reinforces this one being owned by him because it's him, him, me, him. So this one is owned by him now. This one is still in play. So this is him, me. So I'm going to place a green one here to try to own the 7. And he played green there, which now makes it more likely that he's going to own this one, although there is some frustration coming from here and here. So this is a little bit unclear to me who's going to win. Okay, so the last one is here. So this is him and him. So I think that the best thing that I can do here is play a purple to try to lessen the strength of the possibility of both of these always being voting the same as blue. So I'm going to play purple. So I lost, not surprisingly. This is a very strong player, but we can try to take a look exactly what happened. The purple numbers here are the influence scores of the vertex that they're associated with. So that's the one that essentially, is the key thing. And the influence is the sum over the correlations of all of the other spins with the one that it's listed by. So 1.35 is the sum of the correlations of all of the other sites with 1. Remember, correlation is, +1 if they're always the same, and 0 if there's no correlation at all, and -1 if they're always opposite. So purple can be negative or positive. And whoever has the higher purple score wins. So vertex 1 has a score of 1.35, and I have a score of -0.624. So his is higher than me, and therefore he wins. We can try to trace through why we lost by looking at the blue and the red numbers. The blue numbers are they're a correlation score between the vertex and the color that they represent. So 17 has a 1.67 correlation. It's not actually correlation because correlation is normalized between +1 and -1, but this is some kind of unnormalized correlation. I can't remember exactly how I did it, but basically the more positive the number is, the more positively correlated they are, and vice versa for negative. So you see, like, all of the ones in the clump, the ones that are connected by green, all have positive correlation scores, but they vary in magnitude. And the reason they're positive is that they're all in the same ferromagnetic clump. The reason why they vary in detail is that not all of the members of the clump have the same likelihood of voting together. So for example, if you look at 11, it's technically in the clump, but it's actually a negative with blue. And that's because of the influence of the other two vertices and what they are on it. So it doesn't vote with the clump, even though it's got a shared leg with the clump. Likewise, the purple vertices tend to give you negative correlations because they want to vote opposite. And so, for example, 2 is negative with 0 because there's a purple link in the middle. So you can trace through and look at who's got the highest correlations with you, and you can try to figure out why. For example, 4 and 9 and 16 are very highly correlated with me, and that's because they're very tightly ferromagnetically coupled. So are these two. So all these ones that I said were in my clump, I won them. That, I have positive correlation scores. But in a close game, usually what makes the difference is the scores that are actually close to 0. So ones that could have flipped one way or the other. In this case, there aren't very many close to 0 scores. They're, more or less all fairly significant correlations, which may actually mean that there's no frustration in this one. It could just be like, I actually don't think that's true. There is frustration, but it might be minimal in this case. But at the end of the day, this particular configuration of edges, which again represents an icing model, when you sample from the low energy states of that icing model using simulated annealing in this case, you get a bunch of ups and downs for each of the nodes. And when you calculate the influence of each of them, you get the score. And in this case, I lost. Again, not a surprise, because with 1,000 rollouts, Monte Carlo tree search is very powerful at winning on this particular board. The rough ELO score that I've got for this particular agent is 2,600. And I'll, in a later blog post, I'm going to describe how I get those numbers and what they mean. But yeah, so here's an example of me getting trashed by an AI again at a game I invented. All right, thanks, friends.